to page 2 of the chain rule. And now what we're going to do is we're going to consider a situation where we have, a function of two variables, but each of the variables x and y is a function of two other variables s and t. And so z is indirectly a function of s and t, and we can take the derivative of this, but now instead of being able to say d like it's defined, now we'll say partial. And the reason why I have to say partial is because there's two independent functions that we're really trying to find, s and t. So therefore, because there's two functions inside the functions that we want, that's why it's not partial instead of just normally defined by d. So in order to get to our partial of s, we'll do the same thing. We'll take the derivative of z with respect to x, or partial of z with respect to x, and then we'll take the partial of x with respect to s. But we also have to do that same thing with our other variable y. So we take the partial of z with respect to y, and then we take the partial of y with respect to s. And same thing with t. So we have to work through our variables. We're just pretty much working through each variable that has s and has t in order to find our derivatives. So case 2 of the chain rule contains three types of variables. S, t are independent variables. X and y are called intermediate variables because they depend upon s and t, but they do not lead to our final. And then z is the dependent variable. So x and y are going to be the intermediate because they're like the middleman. So here's a tree diagram. And so what a tree diagram does is it allows us to write all of our variables. And then, so here we have z, x, y, and then st and st. So z leads to x and y, and x leads to st and st. And so if I want to get to st, I'm just going to follow the path from z. And in doing so, that means that I have partial z with partial with respect to x, and a partial x with respect to s. And the same thing here. I want to get to s, so I'm going to go ahead and use my factor tree. I'm going to have to take a partial of z with respect to y and a partial of y with respect to s. So if I want to find my partial s, I'm going to use all those branches that lead to s from the tree diagram. Again, you don't need this if you don't want to draw it, but it is helpful to determine, how to get to the partial that we want. All right. So now I'm going to go ahead and I'm going to use the factor tree to help solve this. So the first one is we want to find partial z with respect to s. So let's go ahead and do that. So the partial of z with respect to s is going to be equal to, all right, so we are going to take the partial of z with respect to x first, times the partial of x with respect to s, plus the partial of z with respect to y, times the partial of y with respect to s. So those are all those that we need. So now let's take the partial of z with respect to x. So the derivative of e to the x plus 2y with respect to x is just e to the x plus 2y. Times our derivative of s of t, which is just 1 over t. Next we do the derivative plus the derivative of z with respect to y. So this is going to be 2e to the x plus 2y. Times, move up a little bit, times the derivative of s with respect to t over s. So that's just going to give us negative t s to the negative 2 power. All right, and when we clean that up a little bit, all right, we have 1 over t, and then we have it over s squared. I'm just going to go ahead and pull out e to the x plus 2y, e to the x plus 2y. Again, you can clean this up any way you want. I'll be able to determine if you were able to do that correctly or not. And then when we pull that out, we're going to be left with 1 over t on the left minus negative 2t minus, so the minus is taken care of, so 2t over s squared. Alright, now let's go ahead and find the next one. So now the partial of z with respect to t. So that's just going to be the partial of z with respect to x times the partial of x with respect to t plus the partial of z with respect to y times the partial of y with respect to t. Alright, now let's go ahead and find everything. So again, what's nice about this is that, okay, that first part is going to be the same, the derivative of our function with respect to x, so e to the x plus 2y. Now the derivative of s over t is going to be negative s t to the negative 2 power plus the derivative of y with respect, derivative of z with respect to y, which is 2e to the x plus 2y, times, now in this case, the derivative of t, which is just going to be 1 over s. And the same thing, we can pull out an e to the x plus 2y. And then we're going to be left with negative, and we could actually move this to the back if we wanted to. I'm just going to keep it here, negative s over t squared plus 2 over s. All right. And again, if you have any questions, let me know. All right. So that does it. So those are the two partial derivatives. So now next, what we're going to do is we're going to go ahead and just use a tree diagram to write out the chain rule for the given case. And again, we're going to assume that all of our functions are going to be differentiable. So now, doing a chain rule, we got to denote all of our tree diagram using the chain rule. So our big function is r, and now that has x, y, z, and t. So now I'm going to have a branch that goes to x, branch that goes to y, a branch that goes to z, and then another one that goes to t. And now each one of those goes to UVW, they all have UVW. So let's go ahead, and each is going to lead to a U, a V, and a W. A U, a V, and a W. A U, V, W, and a U, V, W. And each of those lines is a partial with respect to what it's heading to. So I'm just going to draw out one, and let's say, hey, let's take the partial of r with respect to, I'm just going to show you how you can use this with respect to one of our independent variables. Let's say v. All right, that's like a middle one. So I'm just going to highlight how we get that. So we're going to go from r to x to v, r to y to v, r to z to v, and r to t to v. And now I'm going to go ahead and write all that out. So the partial of r with respect to x times the partial of x with respect to v plus the partial of r with respect, looks like a 2. That's partial, I'm not going to erase that. The partial of r with respect to was y, and then the partial of y with respect to v, plus the partial of r with respect to z times the partial of z with respect to v, and then plus the partial of r with respect to t times the partial of t with respect to v. And that's how we would take the chain rule. So that tree diagram does help out in trying to find the pathway to take the partial of whatever variable that